All right, let's get the show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1207. Let us jump into it. Okay, so today's the day. Day for test one. Now I know you guys are dying to be tested on this stuff so you can show off how much you know. Well, that starts today. So test one was posted as of 3 p.m. this afternoon, and you have until 9 p.m. tomorrow to submit it. Like I said, I wrote it. I didn't really add anything else, and I told you guys I'll give you guys an hour and 15 minutes, but I threw on an extra 15 minutes just because. So you'll have 90 minutes to do it, and it is labeled math. Well, that's actually a typo. It's labeled math 1207. I mean, of course you know that. Hopefully you know what class you're in. So it's labeled math 1207. Test one. So I posted a bunch of practice tests there. Everything is clearly labeled, so you should be able to tell the difference between a practice test and an actual test. So don't click on the actual test unless you are ready to do it. And don't make a mistake. As you know, the test is up until 7.8, which is numerical integration or something like that. It's either numerical or improper integrals, but it ends with integration. And there are bonus sections on chapter 11. So I might ask you some sequence questions, some series questions, that sort of thing. So things like we've talked about before. So the practice exams are up. You have 5 of them up. So that'll give you a good idea of the kinds of things you will be asked. And today I will I'm okay with reserving the last hour to go over questions that you guys may have. If there are no questions, I'll just continue to teach for the remaining hour. But today is going to kind of be a 2/3 class day or something like that. So those are the main announcements I wanted to start with. Unless there are any questions, comments, concerns. So other than that, we're okay, we're good. Okay. So I guess we will continue. Let's actually talk about what we did yesterday. So yesterday we continued to look at what happens for a sequence to determine whether or not sequences converge. So remember what sequences are. Sequences, right? Not to be confused with series. With both words start with S. Vocally you'll mix them up all the time, but hopefully you know the difference between the two when you see it on paper. So a sequence is just a list of numbers in some definite order. There's a rule or something that tells me what is the rule that gives me these numbers. Usually can be described mathematically, and for us a lot of the times it will be able to be described in a formula. Turns out you can take the limit as n approaches infinity of this formula whenever you can, and if it approaches a real number you can say the sequence converges to that real number. If it goes off to infinity or the limit does not exist or minus infinity, then you say the sequence diverges. And we looked at a very important relationship about how different kinds of functions relate to each other. So when you're going off to infinity, you'll know who is bigger than who. And so you know that logs are very much less than polynomials, very much less than exponentials, very much less than factorials, very much less than things like n to the n. And so this will help you evaluate some limits as you're going off to infinity. And we did a bunch of examples where we determined when limits, when the sequences converged. And this was the relationship I was just talking about. So we know that, and that can be helpful in determining convergence. Convergent sequences follow the limit properties, all the usual limit properties, so that's pretty nice. And it's also going to be useful to know when a sequence is decreasing. This just means each term is going to be less than the previous term. It's actually good enough to be less than or equal to the previous term for most of our situations. And that, someone's coming in here. And yeah, afterwards we started talking about series. Now for us, a series is just the sum of the terms of a sequence. So you have a list of numbers, and the only ones we care about are these infinite lists of numbers. And now you go on and you try to add all the terms of this list together. And when you do that, you are creating what you call a series. So a series is just the sum of the terms of a sequence. Again, there are finite series and there are infinite series. For us, we will care about the infinite variety. And so essentially what we want to do is we want to figure out what would it actually mean to do something like add up an infinite number of terms. And we kind of came up with a criterion by which we will say we have added up all the terms and this is the answer. And a part of that relied on the definition of what a sequence of partial sums is. So the sequence of partial sums is just a sequence, Sn, it's a list of numbers, and Sn is giving the sum of the first n terms of your sequence. So that's what your Sn is. And it turns out this list will actually be a list that will converge to the actual sum of any that you want to calculate. So we actually define our series, if it converges, to be equal to the limit of the sequence of partial sums. Okay, and so that is what we will define. We can say we will be able to add up an infinite number of terms if we can find its sequence of partial sums and they approach some real number. If the sequence of partial sums diverges, we will say the series diverge. And it's very important to know there's a very big difference between a series and the corresponding sequence that it is summing. So we saw, for example, here, this here was like the sequence, this is your an, and an actually approaches 0, but the actual sum approaches 1. So these two are not the same. You cannot take the convergence of a sequence and immediately extrapolate the convergence of the series. It's not that simple. In fact, we kind of know that unless the sequence that you're summing converges to 0, the series will diverge. So as long as your sequence can converge, but if it converges to a non-zero number, then the sum doesn't work. And also the answers themselves can be very different. So that is important for you to know. We went into two important definitions. Again, well, another important definition, talking about the two different kinds of convergence that you can have for series. One is if a series converges absolutely. And this just means you go to the list and you put absolute values around everybody and then you add them up. So there's no negatives. Everyone, you're adding positive quantities or non-negative quantities. And if that series, after you put in the absolute values, if it converges, you say that the original series converges absolutely. It converges with absolute values around all the terms. If the original series converges, but when you put absolute values around it, it doesn't converge anymore, you say it converges conditionally. And that just means it converges on the condition that you don't put absolute values. If something doesn't converge absolutely and it doesn't converge conditionally, it diverges just in general. It can't be added up to anything. And we learned that one of the reasons this distinction is important is because of commutativity of addition. There's actually a theorem called the Rearrangement Theorem that tells us if a series is conditionally convergent, then the answer to the sum can change by rearranging the terms. If something is absolutely convergent, then it doesn't matter what rearrangement you do. You have complete commutativity of addition, and you can actually treat an infinite sum like a bona fide mathematical object. We can do calculus with it, we can integrate it, we can differentiate it, we can take limits of it, and we can do all these things because it behaves just like a real number, just like a real sum. And so conditionally convergent series are not like that. And then we saw some properties of series. We didn't have a lot here because a lot of things don't work with series. So we at least know that we can factor constants out of series, and series distribute across sums. They do not distribute across products or divisions or anything like that, and you want to be careful with that. We also saw a special case of a series called a telescoping series. This is just one in which its partial sums is an expression where most of the intermediate terms cancel out, and this allows you to actually find the sum a lot easier, because you just have a few terms to take the limit of, and then you can get to the sum. And we saw that here. Then we moved on to 11.2 through 11.6. I'm not going to delineate the sections anymore. We're just going to treat this all as one long story, where I'm going to go through some convergent series convergence tests for you. So it turns out, just like improper integrals, sometimes knowing when a series converges and what it converges to is a very difficult thing. This game that we were playing with figuring out, what does the sequence, what expression gives us what the sequence of partial sums look like? Take the limit of that. Or we look at, oh, this sum is telescoping. Let's just expand it out, cancel all the terms that we need, and we can get to the answer. Most series aren't this nice, and it's not that simple to deal with them. And a lot of them, we actually just need approximation with a computer or a calculator of some sort. But we do want to know when that is worth the endeavor, because it can be computationally costly. So we want to know when a series converges or diverges without actually knowing the exact answer to which it might converge. And so that's where series tests come in. So there are a bunch of tests that we can run to kind of look at a series, a random series that we're given, and tell whether or not it converges. Just like how we could use the comparison theorem with improper integrals to determine when an integral converges, even though we don't know how to calculate it, or we don't know what the actual answer is. There is a series test that does tell us what the answer is, and this is when we have a geometric series, which is a series that looks like one of those two forms, either going from 0 to infinity of AR to the K or AR to the N, or 1 to infinity of AR to the N minus 1. You sum a bunch of terms like that. That's called a geometric series. And when those converge, they converge if your R is less than 1 in absolute value, and it will converge to A over 1 minus R. And we did a very clever trick to figure that out with this whole process of, adding Sn to R, subtracting Sn from Rsn, and then solving for Sn, and then taking the limit. We saw that that's what a geometric series does. And because the condition is an absolute value on the R, it means that if I threw absolute values around all the terms, we would still converge. It will not make a difference. And so a geometric series, when you know that a geometric series converges, it will converge absolutely. So absolutely is the gold standard of convergence. This is the one that's really nice. If something converges absolutely, that means we can do calculus with it, and that's awesome. If it doesn't converge absolutely, sure, we can get an answer in a small kind of context, but we can't really do much with it, anything too sophisticated with it. So that's actually a very important and nice thing to know. So whenever a test gives us absolute convergence for free, I'm going to mention it because that's something that's really nice. Usually absolute convergence is something you'd have to test separately, but there are a few tests which you get it for free. So like the geometric series test gives you absolute convergence for free. The ratio test gives you absolute convergence for free. The root test gives you absolute convergence for free. We haven't spoken about the ratio or root test yet, but we will get there. So don't worry if you don't know what those are yet. So far, we've looked at the geometric series test, and we've also looked at a very important kind of test, which is the test for divergence. And remember, as the name suggests, this can only tell you about divergence. You cannot use the test for divergence to say something converges. It cannot be done. So the test was, if you take the limit of the sequence term and it's not 0, and that means not 0 in any sense of the word. It could be infinity, minus infinity, or does not exist. or gives you some other number other than 0, if it's anything other than 0 specifically, then the series of those terms will diverge. And you cannot say convergence from this, right? And so we also looked at two very important examples, which is why the converse cannot be used to make any conclusion. It's possible for the limit to go to 0 and you diverge, and it's also possible for the limit to go to 0 and you converge. So you can't say, oh, the limit goes to 0, so I know something converges. You can't make that conclusion because it could actually go either way. We do know that if the limit is not 0, it definitely diverges. That's all we know, right? We cannot tell convergence from that. So we looked at the test for divergence, which tells you when a series diverges for sure. If you want to know that it converges or you can't make a conclusion, then you have to do some other test. And so when we're doing series for a while, what we're going to be focused on is just learning these different kinds of tests. And it's kind of going to be the same feel like us learning different techniques to apply to integrals. So there's going to come a point where I'm going to give you a bunch of series and I'm going to ask you which one converges absolutely, which one diverge. And you should be able to look at the series, know what test to use to be able to determine that. And so that's kind of where we are. And right now we were with, we covered the geometric series, which is the second test that we're going to do. And we left off with wanting to do some examples. We did one example, which was actually the same motivating example that we used to kind of figure out, could we actually walk a mile by dissecting that mile into an infinite number of halvings? And it turns out that we could. So you take a length, you slice it in half, slice the half in half, slice that in half, then slice, do this forever. If you add those all up, you actually get back the whole that you started with, which is very comforting. That's good. And it turns out that that particular series was a geometric series. So you get a geometric series by you starting with a term, and it doesn't matter what this term is as long as it's not 0, and you keep multiplying that by the same thing. So in this case, it's like we started with a half and we kept multiplying by a half. So a half times a half was a quarter, and then that times a half is an eighth, and then that times a half is a 16th. So we built an entire series in this particular pattern. That is what's called a geometric series. And if the thing you're multiplying by repeatedly is less than 1 in absolute value, that series will converge to the first term divided by 1 minus the thing you're multiplying by repeatedly, right? A over 1 minus r. So that is, yeah, so let me kind of be specific here. So this is your A over 1 minus r. In this case, your A and your R happen to be the same number. So yeah, that is where we are. So want to continue now with doing some more examples on that. So picking up where we left off. So here's the thing. So obviously this series already looks very complicated. So as you might think, just like with integrals, sometimes it's not so straightforward to apply a certain test or a technique. You kind of maybe have to simplify it somehow, or just look at it in a very creative way to kind of figure out something that you would do with it until you get practice with it. And so the same thing is going to apply to series tests. So it's not like, oh, I tell you a geometric series is A times R to the N, and you're summing that. It doesn't mean it has to always look like A times R to the N, like visually to the eyes. Sometimes you might have to do some, a little bit of work. So for example, here, this one, the series N goes from 0 to infinity of 1 plus e to the n divided by 4 to the n plus 1. So this is a series. And obviously, because we're talking about geometric series now, there's going to be a way to use geometric series here. And so maybe you guys can tell me about how you'd want to do that. So remember, a geometric series, it looks like it's either n goes from 0 to infinity of a times r to the n, or it will be n goes from 1 to infinity of a times r to the n minus 1, and if and only if r in absolute value is less than 1, then the series converges to a over 1 minus r. So that's what we know about geometric series. So how would we apply that here? So maybe someone can tell me what is the a, what is the r, how would I apply it, get the answer, or does it even converge? Do we even know whether it converges? It could diverge if your absolute value of r is greater than 1. What do you guys think? Any ideas? Like, what is your a here? What is your r here? Any ideas? No? No clue?
Is it a is equal to 1 plus e to the nth power, and then r is equal to -4 to the nth power plus 1?
1 plus e to the nth power.
And then r is -4 to the nth power plus 1.
Okay, so remember your a here, your a and r are constants, right? Constants with relation to the series. So a and your r, they're not 0 and they're a constant. So the fact that you have n's here means they're not constant. So that cannot be the a and the r. So it's something like, oh, you have a series of 2 times 3 to the n, or you have like a series of 14 times 2/3 to the n minus 1 or something like that. So these things have to be like numbers. The moment they have letters in them, then it's not a geometric series anymore. Right, so it's very, so you have to be careful how you're doing that. So now when I tell you, say that, does that help? Now, of course, I mean, I gave you the definition of what a geometric series looks like. So the first question you would ask yourself is, does this look like that? And I believe the answer would be no, right? You want to be able to write it as a number times some other number to an nth power. And then you tell me what those numbers are. So this is clearly not in the right form to just read off the numbers. Right? You first have to put it in the right form, and then you'll be able to say what the a is, what the r is, etc. So there's actually something going on here. Well, any ideas?
You could negate the exponent for the denominator, but then that would leave you with an n in 2 terms.
What do you mean negate?
I mean, 1 plus e to the n divided by 4 to the n plus 1 is the same as 1 plus e to the n times 4 to the negative n minus 1. So you're negating the exponent to turn it into a multiplication, which makes it closer to the geometric series.
Okay. So something like 1 plus e to the n times 4 to the minus n plus 1.
Yes.
Okay. And what do you do with that? So there are a couple of things off here, obviously. The negative power isn't a thing. And this isn't a constant. So, I mean, if you wanted to do something like that and write it as a multiplication, you'd actually still leave the 4 in the denominator. So, I mean, something like this you could do. That would be closer. All right. And now what? Do you see anything to do after that? Because I mean, we're starting from 0, which means we'd probably want it to look like this version. What should the power be in that version? The power you should have is n. And notice here you have the power n plus 1. How would you deal with that? Any ideas? So we have to work on our algebraic manipulation skills, and I guess sort of remember how powers work and things of that sort, and realize, you know, you get addition in power when you're multiplying things. So that should be one thing you would notice. So for example, like a 4 to the n plus 1 power, where would that come from? Well, a 4 times 4 to the n, right? So that's probably one of the first things I would do, because I know my definition, the thing I want it to look like, has the nth power. So if I see a power other than n, I don't want it to be anything other than n. I want to transform it to n. So I see one of these things as an n plus 1 power. Oh, that just means I'm multiplying the thing times itself to the n. That's where an n plus 1 power would come from. Now, I also know by a property of series that I can factor constants out. So I can take a quarter, factor this out. And so now I have that. Now I want to write something to an nth power. Now, obviously in the numerator, only the e has the nth power and the 1 does not. So probably the next thing I'd want to do, split these up. Now, again, I know what I'm aiming for. I want something times something to the nth power. I don't want 1 over something to the nth power or something to the nth divided by something to the nth power, right? I want to write it like one of these forms. But again, I know how exponentials work. So it turns out that 1 over 4 to the n, I can write that as like 1 over 4 to the n, because 1 to the n is always 1. And of course, e to the n over 4 to the n, I can write that as e over 4 to the n, because powers distribute across division. Now, I know by another series property that series actually distribute across sums. So here, I can say that this is going to be the series of 1 over 4 to the n plus the series of e over 4 to the n. Now, of course, I know that this should be a times r to the n, which now it is. It's just that, you can imagine there's like a 1 multiplying here. So this is a geometric series with your a equals 1 and your r equals a quarter. And this is a geometric series with your a equals 1 and your r equals e over 4. These are all constants. Now, what can you tell me about a quarter and e over 4 in terms of the condition that I would have to check? I would have to check that in absolute values, this thing is less than 1, right? So does a quarter fit that description? Is a quarter less than 1 in absolute values? Yes, no, maybe so. Right, so if I put r in absolute values, that's just a quarter in absolute values. Is that less than 1? Yes. So that means that does converge. And I know, in fact, that that means it converges to a over 1 minus r. And here we have r in absolute values. That is equal to e over 4 in absolute values. Is that less than 1? E over 4. What is e roughly? Because that's actually something that's important to know. You remember what e is roughly?
I think it's just above 2.
Right, so e is 2.718, right? So you have 2.7 divided by 4. that is going to be less than 1. So this also will converge to a over 1 minus r. So it turns out that this part, the a is 1, the r is a quarter. So this is going to go to 1 over 1 minus a quarter. Plus here the a is 1, the r is e over 4. So this goes to 1, it's 1 minus e over 4. And all of that is times a quarter on the outside. So I can do is I can actually simplify this. I can do something like multiply by 4 over 4. And so that would give me 4 minus 1. So that would just be 3. So this is just 4/3. And so that's actually a quarter as well. And then here again, I would multiply by, say, 4 over 4. So that would become 4 over 4 minus e. Or in other words, I can write this as 1/3 plus 1 over 4 minus e. So this series does converge. And I actually know exactly what it converges to. It converges to 1/3 minus 1 over 4 minus e. And it, by the way, it converges absolutely to this, which means even if I were to write out the terms and rearrange them, that is still going to be the answer at the end of the day. Okay. So that is this one. Can apply the geometric series. And so with the geometric series, you'll always actually be able to find the answer. Or it diverges, in which case you don't have an answer, right? Let's move on to the next one. What about this? Based on the lessons that we've learned before, tell me how to do this one. Ideas now? It's actually a bit easier than the last one. If you learned the last one, the lessons from the last one can pull you through this one.
Is this one just geometric?
How would you know? What would the a and the r be? Right. So when you say something is geometric, you're saying it looks like this or it looks like that. That is precisely what you're saying, which means you should be able to tell me what the a and the r are. Right. So what would they be here? Does that look like that? Does this look like?
No, it doesn't. We have to do manipulation.
Does
but I
this look
don't
like
know
a constant
how.
times a constant to the n?
No.
No, right. So we have to do something. What can we do here?
You can pull out an E over pi.
And we'd have what left?
1 over pi to the n.
And how would you write that in the right form?
In this case, since it's a 1 over pi, I think that's just equivalent to 1 over pi quantity to the n, like in parentheses. So you can treat that as the
Yeah,
R term.
1 over pi to the n. Right. And so again, that's geometric here. So here it's like your A is 1, your R is 1 over pi. And by the way, 1 over pi is less than 1 in absolute values, because pi is 3.14, right? And so this will converge, and it will converge to A over 1 minus R. That's where we are. So these are the things you have to be able to do with these series, because a lot of times the form is actually going to be important for you to pick certain things out. So you should actually know, oh, this is the template of what a geometric series is. And I cannot conclude that anything is geometric unless I can algebraically manipulate it to fit that template exactly. And once it fits that template exactly, the rest should be easy. It's just a matter of spotting something that could be written as geometric and then moving forward from that, and knowing how to manipulate with powers and exponents and factoring things outside of series or splitting a series across a sum, because you can have things that are partly geometric and partly something else, just like with integrals. Like you'd have the integral of a sum, so you split the integral across the sum and you'd have a different technique on this one than on that one. So that sort of thing is going to happen with series as well. So you really have to kind of know what the form is that you're looking for and how to manipulate things to look like that form so you can actually apply the rule. But this one, 1 minus 3 over 2 plus 9 over 4 minus 27 over 8. Does anyone see what the A is, what the R is? So this is geometric, we know that for sure. So what is the A? Or like definitionally speaking, what is the A? What do we say A represents? Do you remember that? Yes, we don't remember. No, we don't remember.
It's the constant multiple.
No, that's the other way. A is the first term. Right? So if this is a geometric series, A just means the first term. And I can look at this and know that the first term is 1. Now, R is what's called a common ratio. That's the thing that you keep multiplying by over and over. Do you see what that is here? Here, that's minus 3/2. So notice that here you have 1 plus 1 times minus 3. One plus 1 times minus 3/2. Then plus, you have multiply again by minus 3/2, you get minus 3/2 squared, which is actually positive 9/4, plus minus 3/2 cubed, that'll be negative 27/8, etc. So the thing we're multiplying by repeatedly is minus 3/2. So here you would have A equals 1. And your R equals minus 3/2, which, by the way, if we were to put absolute values around the R, that means absolute values around this, which is 3/2, which is actually bigger than 1. So what does that mean for our series? What does it converge to? It converges to nothing, it diverges. Because your R in absolute values is greater than 1. So those are the last remaining examples for geometric series. And that's where we are. Okay. So I don't know, how long is it going to take me to do the next section? Yeah, I'll keep going. All right, so that is the geometric series. Those are a few examples. Let's move on to the third test. The next thing we're going to do is called the integral test. So this is I think it's the third test in our table. I'm going roughly in order at this point. Yeah, integral test, third test in the table. We're doing this guy. So now suppose you have a series AN. Notice that it can start from anything. So generally it's going to start from some positive number, either 0 or some positive number. Right? And so here's what we do with the integral test. Let's say the AN has a formula which we know can integrate. We can integrate easily. And on top of that, the function that we can integrate easily is eventually a decreasing function. And remember, we now know how to test if something is decreasing. Okay. So if we have these conditions, as well as the function is always positive, because there's going to be a thing with the integrals where it dips under the curve and that can cause some issues. So if a function is positive, it is continuous because we can integrate it and we don't have to worry about improper integrals or the fact that the fundamental theorem of calculus will stop working, and it's decreasing. So it's positive, continuous, and decreasing. And let's just say on top of this, it is a function that we could integrate. Then it turns out we can actually use an integral to determine what will happen to the series. So like the series n equals a to infinity, we will instead consider the integral from a to infinity of the same formula, right? And it turns out you can actually use what this integral does to figure out what the series is doing. So the idea is the following. So remember the series, we saw that series they had these discrete gaps. So essentially we're pretending that that's not the case anymore, right? So I'm gonna draw some pictures to kind of illustrate to you the idea that we're going to run with here, right? So say we have some function that describes it, right? F of x, right? But remember, your series will not be the whole thing. They're just going to be some like isolated rectangles, which we're using. But we're actually going to put this on steroids, and we're going to do some bona fide Riemann sum integrals. Okay. So we're going to do it in such a way that the area under this rectangle is actually equivalent to the value of the AN. So we do a rectangle whose area is about the magnitude of A1. So think of A as being here. This is A plus 1. So let's say you have another rectangle here. And we're deliberately doing the rectangles underneath because it's decreasing. We can actually do this. This is A plus 2, A plus 3, etc. Right? And so there's an area here, and there's an area here. Right? So there's the area of these rectangles that's underneath it. Right? So the area of this one, the area is the magnitude of A1. This one, the area is the magnitude of A2, and so forth. So we can actually construct things of this type underneath it because the thing goes on forever, right? And so we can actually do this. Now, it turns out we can actually do something that's kind of like the comparison theorem. So notice that the white shaded area has to be greater than or equal to the green shaded area, no matter how many rectangles that I use, which tells me that if the white area converges, it actually adds up to a finite number, then the green area needs to converge as well. And so basically, if the integral converges, it's bigger than you would need for the series to converge because it's filling in more stuff, right? So if the integral converges, it forces the series to converge. So that's sort of the idea here. You know, if the white area converges, right, i.e. the integral from a to infinity of f of x dx, then so does the green area. I.e. the summation from a to infinity of an by the comparison theorem. And so you see that if the integral converges, the series will also converge. Now you can do this in another way. You can, starting from a, let's make this a plus 1, a plus 2, And this is going on. This time, what we can do is we can put the rectangles above. You know, kind of switch to like a left-hand rule kind of thing. So again, we have the area under the curve, which is going to be given by the integral. And usually you can actually accomplish this by shifting the rectangles a little bit. So from shifting under to over, you just kind of slide everyone to the right to move them over the guide. And because the function is increasing, so you can just, you know, take the first term separated and shift everyone over to the right, and you'll get someone that's bigger. So here, let's say the green area is this. And again, you can know the following, that if, again, by the comparison theorem, if the wide area diverges, i.e. the integral diverges, then so must the green area, i.e. the series. So here's where you kind of end up. If the integral converges, you can actually show that the series will converge. And if the integral diverges, you can show that the series will diverge. In other words, this guy converges if and only if that guy converges. And so you end up in this situation where you can actually tell what the series is going to do by looking at what the integral is going to do. So you can actually set up an integral, an improper integral, and we know how to solve for those now. And we can actually use that to determine whether a corresponding series will converge, provided that the series has certain conditions. If you imagine the formula for the sequence is not just plugging in integers, but you can plug in any real number. So you just pretend it's just a continuous function, and it's positive, decreasing, and continuous. Then if you can integrate it, it turns out that the integral will actually tell you about the series. They'll actually both diverge or they'll both converge. This actually leads us to what we call the integral test, right? So under these conditions, you can actually determine what the series is doing by what the corresponding improper integral is doing. And so that's right. So that's what basically this is saying. Under these conditions, we can know what the series AN is doing based on what the integral does. So we've just turned a series problem into an integral problem eventually, because the integral is both, you can consider it as both being below and above the series by how you construct your rectangles. And so when these two, like, they hug, the integral curve hugs the series curve. And so you can actually talk about what the series is doing based on what the integral is doing. And this is actually like an advanced application of the comparison theorem, because you translate the entire problem into playing around with areas. And so once you're talking about areas, you can talk about integrals, because you're talking about areas under a curve and approximating this with areas of rectangles. So this actually puts us in a nice position to actually do this. Now, this works in general once these conditions are fulfilled, but of course for you, or for us, we really can only apply this if we actually know how to deal with the integral. So there's like an unspoken condition here where it's like you should be able to integrate the f, right? If you can't integrate it, you don't know how to deal with the integral, then this test is actually pointless. So if you see these conditions, but the f of x isn't something that you know how to integrate, or you don't know how to talk about that integral, then it kind of doesn't even make sense to apply this test. And that's going to be one of the reasons you can know when you might want to use the integral test. So essentially, if you look at the formula and you're like, I could actually integrate that pretty easily, and that might be something I want to try, then that will help us determine what the series is doing. So, for example, determine if this series converges or diverges. Now, this is one of the things where the integral test can work, because if I look at that expression, right? So if I imagine like my an equals f of n equals e to the 1 over n squared. So that means my f of x would look like e to the 1 over x squared. Now, of course, you know a few things. Since we are on the interval 1 to infinity, right? Because we're integrating from 1 to infinity, then we have a couple things. The exponential is always going to be positive, and x squared is always going to be positive. So our function is non-negative, right? So we have that f is greater than or equal to 0. So that was one condition. Also, f is continuous, right? It's a division of continuous functions where the denominator is not 0. And so we learned in Calc 1 that if you divide continuous functions, it's continuous everywhere the individual functions are continuous and where you're not dividing by 0. And moreover, also, if you look at f prime, so this will be the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. So this is like e to the 1 over x times minus, I can actually factor out a negative here. Minus e to the 1 over x times 1 plus 2x over x to the 4th. And that is negative. So this means f is decreasing. So I know my f is continuous, I know it's decreasing, I know it's positive. I have all the conditions needed for this thing. And on top of that, there's actually something very nice about this guy. See, this function here, e to the 1 over x squared, is actually pretty easy to integrate. It's something that hopefully it's pretty easy to integrate. We have a test today, so hopefully by now that looks like something that's easy to integrate. Substitution would do it, right? So moreover, if I look at the integral from 1 to infinity of e to the 1 over x squared dx, then what I would do is like a u sub u equals 1 over x, or du equals minus 1 over x squared dx. And so you get minus the integral, x goes from 1 to infinity of e to the u du, which is just e to the u. X goes from 1 to infinity, which is just e to the 1 over x from 1 to infinity. Now, technically, this is an improper integral. I should be saying, oh, limit of x approaches infinity, right? But at this point, we're just gonna do it very informally. If you plug in infinity into the x, you get e to the 0, which is 1, and then minus, which means you plus. You plug in 1, you get e. So you get e minus 1 as the answer, and that, of course, means there's another test coming up here, and that, of course, means I converges, where I'm going to call this integral I, and therefore I can say that the series converges. By the integral test. Okay. So anytime I see something where if I pretend the formula for the an is just a regular continuous function that I'm used to dealing with in calculus, and I know that it's continuous, it's positive, and it's decreasing, then if I can actually do an improper integral using the same limits as the series, if I just do an improper integral like that, then whatever the integral does, the series will also actually do. So if my integral converges, my series will converge. My integral diverges, my series will diverge. And that is what the integral test tells us. So we actually can use integration to talk about series under this specific set of conditions, right? So if you didn't have one of these conditions, if you realize, oh, your function eventually becomes negative at some point, or your function is increasing, then this actually doesn't work. Like, you can't actually do this. But yeah, so you look at a series and you see that, oh, the formula kind of looks like something I could integrate easily. And this is going to be assuming that you tried some of the other stuff that I would have told you to try before the integral test. So if you look like, oh, this looks like something I can integrate easily, then you do the check. Is it continuous? Is it always positive? Is it decreasing, right? So you can like check the derivative, see if it's always negative. And it's good enough to be eventually decreasing. So I did mention that here, eventually decreasing, which means it could rise in the beginning, but then if eventually it starts just going down, that's fine, right? You would just take this area, chop it off, put it to one side. Okay, we know that adds up to this. And then you do the integral test on this part right here, and it's going to be fine. Well, you wouldn't have to specifically do that, but theoretically, that's what you would do. You could actually just integrate from this point onwards, and it'll actually be fine. It just has to be eventually decreasing. So there has to come a point where it is decreasing from that point onward forever. And then you can actually apply this test. So we will take a break there, quick 5-minute break, and I will see you guys. All right, let's continue. So we just spoke about the integral test. And now I want to talk about another test. So there's actually a test called the P-series test, which is pretty neat. And if it sort of reminds you of something else that we've seen so far, that is not a coincidence. Well, I guess, would it be a coincidence? I guess it's sort of a coincidence, because it turns out we are going to use what we learned from the integral test to look at this guy. And if you see that 1 over n to the p, and you think, oh, if I'm going to use like a function to talk about this sum f of x, obviously the function would be 1 over x to the p. And so we can, in this scenario, kind of compare this to another integral, which we know a lot about. We actually know how that integral works. So these are, I probably do want to make sure that we understand what these people are. So here, it's very important that you know that your p is a constant. It's a number, right? So it's like 1 to infinity of 1 over n to the 5, or like 1 to the infinity. of say 1 over n to the pi or something like that. It is not, if you see like 1 over n to the n squared, that's not an example of what we're talking about, right? Or 1 over n to the n. Not an example of what we're talking about. It's 1 over n to a constant. So your p is a constant. So any series that looks like this, we call it a p series, right? Now, as I mentioned here, if we think of the an as 1 over n to the p as a function, the corresponding function would be 1 over x to the p. And of course, since our x is not 0 because it's starting at 1, this function is continuous. Also, you can graph it and you'll notice that it is decreasing for positive x. Also, it's always going to be positive itself. The output will always be positive when the x is positive. So it actually fits the criteria for the integral test. And so it turns out that we can actually talk about what this series does based on what the corresponding integral does. So this improper integral corresponds to the p series, and that improper integral is actually a very famous improper integral. It's one that we have a theorem for, and we actually know exactly when that converges. We know that that converges if and only if p is greater than 1. So that leads us to what we call the p series test. So if you have a series that looks like this form specifically, it converges if and only if your p is greater than 1. And we actually can know that from the integral test, right? Because the corresponding integral would be this guy. And we know that that guy converges for p greater than, strictly greater than 1. And so the integral test actually gives us another test that falls out. And notice that this will actually give us a proof for why those two important examples that I mentioned yesterday, why they work, why the harmonic series diverges, right? So remember the harmonic series. This is just the series 1 over n. Right? Or you can think of it as 1 over n to the 1 power. In other words, it's a p series where the p is equal to 1. And so by the p series test and by the integral theorem that we have here, that will diverge. However, 1 over n squared, this is like a p series where the p equals 2. And since p is greater than 1, that guy is going to converge. So it turns out a very easy way to actually look at the two examples that I mentioned yesterday was using a p series. And we know that those guys converge. We know when those guys converge based on the integral test. And so we can just use this as a test onto itself. We know when guys like this converge. So here are some examples. So suppose you see a series like this and ask you, does this guy converge? Well, one thing you can notice is that this is equal to 1 over n to the 1/2. Now, it is important for you to notice also, because we don't want to even mix this up, that you would not want to write it as 1 over n to the 1/2 and then just think, oh, it's some sort of weird geometric series, because it doesn't look like a geometric series. For the geometric series, the base needs to be a constant, the power needs to be a variable. This actually happens commonly in calculus, so I just wanted to mention that. There are a lot of students who, they think that differentiating like x cubed is the same as like differentiating 3 to the x. These are two very, very, very different functions that apply very different rules, right? So this one would give you 3x squared, and this one is 3 to the x ln 3, right? So it matters who's a constant from who's a variable. So if your power is a constant, the base is a variable, it is not geometric, right? It has to be something else. So I just want to make sure that you're aware of that. That's why I'm always pointing out who is the constant here, who's a number that's not moving. It's not something that's changing in value. The p is a constant. And with the geometric series, for example, the a and the r are constants. And it's very important that you know those, because it's not only important in identifying the kind of series you're looking at, but it's important in how you get to the answer. Okay, so this you will realize that you can actually write that as that. And here you can just see that, hey, this is a P series. With P equals 1/2. Now 1/2 is less than 1. Therefore, it diverges. And that's it. Right. So look at this guy. I know a bunch of forms in my head. Okay, I know what a geometric series looks like. I know what a P series looks like. I know what all these other things look like. And I will be able to say, oh, this is actually a P series, this guy. And once I know that it's a P series, I know how that works. Here's another example. Right? N to the minus 11 over 10. Right? So then I would just write that in a special form. This is 1 over n to the 11 over 10. And then I can say, oh, this is a P series. With P equals 11 over 10. And guess what? That's greater than 1. Therefore, I can say it converges by the P series test. I should probably be specific here, because generally I am going to want you to identify what test you're using. So I have to write out what I would expect you to write out by the P series test. Okay. And that's that. So, I mean, so you might be thinking, oh, those examples, that's awesome. Those examples are simple. And that's pretty much all I want to say about P series tests, actually. The important thing is, generally speaking, the P series itself is not going to be the issue. So generally speaking, you're not going to just be, I'm not going to just give you a series that's a P series. That's just way too easy to actually see that. But it turns out there is also going to be a convergence comparison test for series, just like we had for integrals. And the P series is actually very useful in making comparisons in the same way that that integral 1 over x to the P was very useful for comparison, right? I could take a whole expression. I don't know, did we do it yesterday? Maybe it was the day before, where we could have an entire expression that was like this complicated polynomial, but then I compare it to something that looks like 1 over x to the P. And just comparing it to that allows me to make a conclusion that was just very difficult to make in the beginning. You're going to use P series in very similar ways. So it's not going to be something where, oh, it's difficult to see that this convergence. P series they're easy to tell they converge. You write as 1 over n to some power, and you're like, oh, the power is bigger than 1, or the power is less than 1, the power is equal to 1, and you can know what the answer is going to be. So it's not going to be difficult to do all on its own. What's going to happen is you're going to be given a series that looks way too complicated, and you're going to sometimes want to compare that series to a P series. So the P series, you'll be able to identify what it does very easily. And then based on what the P series is doing, you'll compare it to your original series and you can figure out the answer very easily. So that's sort of the idea. So that is the P series and how you know they converge or not. So I do expect you to know that test. So speaking of comparison, that is actually the next test I want to talk about. So we have a direct comparison test. And you can sort of, again, technically, you could prove this with the integral test, right? So you kind of prove that the integrals will behave. You can determine how the series will behave based on how the integrals behave. And so this kind of sets up the same way that the integral test sets up. So you have two positive guys that you can arrange like this. So this sort of reminds you of the 0 less than or equal to the integral from something to infinity less than or equal to the integral from something else to infinity. And based on what's going on with these two, you can actually know based on what's going on with one of these series, you can know what's going on with the other one. So for example, if the bigger series converges, you know that the smaller series has to converge. Likewise, if the smaller series diverges, I guess you shouldn't say the word likewise. On the other hand, if the smaller series diverges, it will force the bigger series to diverge because the bigger series always has to be greater than or equal to that one, right? And so you can actually know about, you can know what's happening to the AN if you know that the BN is converging because the AN will be forced to converge. You can also know what happens to the BN if you know that the AN is diverging because that will force the BN to diverge. You cannot make a conclusion in any other case, right? So this is just like the direct comparison theorem for improper integrals. So you can actually do this, a very similar thing with series, because the integral test teaches us that we can kind of look at under specific conditions. You know, if I pretend this thing was decreasing, positive, and integrable, we can do that, use integrals to apply to these guys. The same thing holds for series. Although this is a little bit more general because we don't even care if the guys are decreasing or not. It actually won't matter to us. So here is one. So that looks like a very complicated looking thing. So what we would do is not actually do this guy directly. Okay. So you look at this, for example. And one thing you would immediately notice, hopefully, after not too much time, you'll notice that test for divergence would not work. You take the limit of this guy as k goes to infinity, that actually goes to 0. So we can't make any conclusion. It's not a geometric guy because all the bases, some of the bases have variables in them. So we don't have any constant bases to variable powers. In fact, we have the opposite. We have a variable base to a constant power present here. So it's not geometric. Integral tests, come on. What are we going to know? We can't integrate that. We don't know how to integrate that. None of our integration techniques can do that. However, we have a comparison theorem. And we also learned that when you're going to infinity, only the bigger guys matter. So we see this and we know that nothing else that we know about would work so far. So we kind of focus our attention on what these bigger guys are doing. And so this kind of hints to us that, hey, we might want to compare this to the series where just the bigger guys are present. Well, maybe I'll start this from 1 to infinity. So technically, if I plug in k equals 0, notice this would just be, if I plug in k equals 0, I would just actually get 0. And then I can start adding things from k equals 1 onwards if I wanted to. So notice that when I cut it down, starting from 0 is problematic because I would divide by 0. So I would actually want to start it from 1. And that's actually okay because I can separate the constant term that would have made it would be bad in the comparison case separately and just worry about from 1 onwards. If 1 onwards converges, then of course the entire thing converges because then I'll just add a constant to that entire thing. And in this case, the constant is 0. So I can just start this from 1 to compare it to. So technically I'm comparing this to 0, 0 plus this, but I'm only focused on this series now. Now, what is that series? Notice that I can factor out a constant, 3 over rad 2. So very lucky that we have that property. And we would be left with k over k to the 5 over 2. Of course, that would be 3 over rad 2. And I can think of this as 1 over k to the 3 over 2, right? By just knowing how to deal with powers, right? So k divided by k to the 5 over 2 is actually k to the 1 minus 5 over 2. So it's 2 over 2 minus 5 over 2, which is minus 3 over 2, which I can write as 1 over k to the 3 over 2. Now, what do you notice about that guy is that that is a p series. So what I can do here is notice that if our AK is the, someone's coming. If our AK is the original guy, this is 2k to the 5th plus 2k plus 1, and I let BK be this guy, then of course we would have that both of these guys are greater than 0, but the AK is actually less than or equal to the BK. How do I know that? Because I got this guy by taking rid of this denominator here. Right? And technically, I mean, I guess I want to keep the 3 over rad 2. So here, to get to this, to get from this one to that one, I made the denominator smaller. Because 2k plus 1 is a positive number, and I took that away from the denominator. And so this, the BK, the second thing, is clearly bigger than the first thing. And so that actually means that the sum of the AK would be less than or equal to the sum of the BK. And we know that the sum of the BK converges because it is a P series with P equals 3 over 2, which I know is greater than 1. So we have this theorem, and we can actually apply that I'm in the case where this is true. So I would be able to say then the series AK converges by comparison. So this is one of the uses of P series, right? So usually they're not going to be something where, like, in isolation, you're going to need to know about them. Well, you should know about them in isolation. But when it comes to applications, they're most useful when it comes to comparing them to something else. So you want to be able to take something complicated and reduce it to a P series, and then you can, based on what the P series is doing, see what the original thing is doing. And so that is what we can do. So that's nice. Now, you might also remember that we had 2 comparison theorems for integrals, where only one of them needed us to know who was bigger than who. And so we had the direct comparison theorem, or just comparison theorem, and that required us to know which integral was bigger than the other one. And this is the same, right? You have to know who is bigger to be able to make these conclusions. And we looked at, and we saw that there was another comparison theorem called the limit comparison theorem, in which you didn't necessarily need to know who was bigger than who in order to make a conclusion, but you could kind of compare them to each other and see, if you take the ratio, do they behave like a constant? So one just behaves like a constant compared to the other one, a constant factor times the other one as you go off to infinity. And so we can actually look at two things and compare them without knowing who's bigger than who. And under certain conditions, we can actually make some nice conclusions. So we have actually the same thing for series, right? So there is actually a limit comparison test for series. This is the 6th test, right? And again, it's just like us looking at integrals with the limit comparison theorem, right? So I have two things that are strictly greater than 0 because, you know, I'm going to do a division, so I don't want them to be able to equal 0. If I take their ratio and the limit as n goes off to infinity and I get a positive real number, then in that case, I can make a conclusion, right? If the first thing doesn't happen, I can't make a conclusion. But if that happens, I can make a conclusion. The an and the bn will do the same thing. They will behave the same way. They essentially, one behaves like a constant multiplier L times the other one, is essentially what that is saying as you go off to infinity. And so they're both going to converge or they will both diverge. And the idea being, you will know about one of these ones. You will actually know that one converges or one diverges. And so that will help you talk about the other one. Now, there are actually two more parts of the above test. They don't really come up in Calc 2 that often. Usually this is what you need to know for Calc 2. But I should just tell you, generally speaking, that you can sort of make some conclusions if your L is 0. I don't actually remember if your textbook mentioned this. But this is just like some general knowledge. In the event that your L equals 0, you can make a conclusion. And in the event that your L is equal to infinity, you can make a conclusion. This was actually true in the integral limit test as well. I never really tested you on anything where you would need to know that, but you can actually know that's true. So let's do another one. Does this series converge? Okay. So again, we're going to play the same game, right? So none of the things that I mentioned before work. And so I'm going to want to do some sort of comparison. I want to compare to this. Look at the biggest guys. So I'm going to compare to the series n goes from 3 to infinity of n over n squared equals, obviously that's simplifies to 1 over n, which tells you that's a harmonic series. We know that this will actually diverge, right? So now here's the thing. Let an equals the original guy, n plus 10 over n squared plus 2n plus 3, and your bn equals 1 over n. Then you will notice it is not clear if an is greater than or equal to bn, or bn is greater than or equal to an, right? Why? Because look at what happened to go from one to the other. I had to ignore a plus 10 in the numerator, which means I made the numerator smaller to get the new one. So that should make the entire fraction smaller. Okay, awesome, that's clear. However, notice that I also had to get rid of the 2n plus 3. That had to be ignored, which means I also made the denominator smaller. But if I make the denominator smaller, the overall fraction gets bigger. So I made a change that you can talk about. It makes the fraction smaller, but it also makes the fraction bigger, and it's not sure, you're not sure which one is going to win out. I mean, you can go into some sort of argument, but you probably don't want to waste your time here, right? So because losing the 10 in the numerator makes the fraction smaller, but losing the 2n plus 3 in the denominator, makes the fraction larger. So then you're like, well, I mean, who wins here? Right? It's not good enough to say, I feel like the 2n plus 3 in the denominator has a greater effect than the plus 10 in the, it's not about feelings. Like you'd have to prove, if you want to actually justify that, you'd have to prove it if you're doing this in a math class. But that is not going to be clear, or you'd have to do some extra work, which to me in practice is just, it's not worth the time investment. So I would say not do that, not even worry about who's bigger than the other one, just jump straight into the limit comparison test. It's very easy to see that they're actually both positive. So your an and your bn are positive. So that's good. And well, for the n's in question, for n greater than or equal to 3, right? So you have to be positive on the thing that for all the n's that you're considering. So here from 3 to infinity, right? And the limit of an over bn, well, that's going to be n plus 10 over n squared plus 2n plus 3 divided by 1 over n limit. So that's actually the limit of n squared plus 10n over n squared plus 2n plus 3. We know that that limit is 1, ratio of leading coefficients. So that is actually greater than 0, and it's a real number. So I took the limit of the ratio, I got L. L is a positive real number, so I got 1. So that tells me that both series will do the same thing. But we know the series Bn diverges. It is harmonic. And so then we can actually make a conclusion here. The series An, the original series, diverges by limit comparison test. So that's what we have. Any questions on that? I do want to, I think I did want to mention something. Yeah, so for the integral test, because our function is always positive according to the integral test, it means that if you were to throw absolute values around it, it won't make a difference. So the integral test is also one of those tests that gives you absolute convergence. So I probably should mention that. If convergence is shown, it is absolute convergence. So I probably do want to mention that. This brings us to another test. Test 7. So there's another series form that we can look at that doesn't really have any distinguishing characteristics in terms of the actual formula that you see, but what's distinguishing about it is the signs. The fact that the signs alternate. So you'll have plus something, minus something, plus something, minus something, plus something, minus something, plus something, minus something, or vice versa. But it alternates every time. So we actually saw the guy that gave us that, this -1 to the n, or something like this, -1 to the n plus 1, or something like that. In fact, -1 to any odd power will actually have this effect. Any power that will only output odd numbers will have this effect. So there's that. So we're assuming that our an, the base formula, is something that's positive, so that these signs actually alternate. Because of the a's, some of them are negative, and they coincide with another negative sign, you can end up with a positive somewhere where you don't want a positive. So we're assuming that other than this -1 to the n that's changing the signs, the base sign is positive, right? And that allows us to get an alternating sign. We'll get something that looks like this or this. All right, when you start adding up the series. Okay. So whenever you have something like that, you have what's called an alternating series. You have signs alternating. Right? So if it's written out in a list and you notice that the sign change on every term, that's an alternating series. But if it's written in compressed form in sigma notation, you're going to see something like a -1 to the n usually, right? But anything that causes a sign change, -1, minus, plus, minus, plus, minus, plus is good enough. So the test here is actually pretty nice. The alternating series, if these two conditions are fulfilled, then the series will converge. And I would say, make the comment, since I was making comments about absolute convergence. Because there's a sign change, you can actually make things different by throwing absolute values around stuff. So this is conditional convergence. Absolute convergence, but would require another test. The sign changes. Put this in another line. The sign changes mean that absolute values would change the sum, right? it makes a difference if you're adding a +2 versus a -2. So you have something alternating and it's going to land on a -2. Then if you throw an absolute value around it, it now becomes +2. And that obviously makes a difference, right? You can't just think that, oh, the original one working out means that me throwing in absolute values is also going to work out. You can't actually make that conclusion. So when you're doing the alternating series test, it's important that you realize that you cannot determine absolute convergence from this test. You can only determine conditional convergence. But the convergence is actually pretty easy. If it's eventually decreasing, which means after a while, your an plus 1 is always less than or equal to your an, or after a while, your derivative an prime is strictly less than 0. If that happens after some point, and that continues to happen forever after that, then all you have to do is do like the test for divergence. And in this case, that will actually tell you that it converges in the alternating series situation. So if you notice that it's decreasing, you have an alternating series, the terms are decreasing, and the limit approaches 0, that series will converge. It converges in the conditional sense. So, for example, here's another famous series. This is actually the alternating harmonic series. So this goes, it's like, I don't know, I kind of wrote it maybe. This is like -1 plus a half, or it could go vice versa, 1 minus a half, minus a third, plus a fourth, minus a fifth. So the cat was doing something crazy, right? Plus minus da da da. Okay, so it's just like our harmonic series, 1, a half, a third, a fourth, a fifth, etc. going on. But now you have alternating signs. This is also a very famous example because this one, based on the alternating series test, actually converges. And it converges conditionally. So here we have -1 to the n an, where our an is 1 over n. And you know that your an is positive for your n greater than or equal to 1. You also know that your an is decreasing. We saw this last time. And so, if you check the limit of an, well, that's just the limit of 1 over n, and that equals 0, then I can say that this series converges. Converges conditionally, in fact, by the alternating series test. So the harmonic series diverges. It turns out that the alternating harmonic converges. And in fact, it converges to something. It's another one of those weird things where you're just adding up a bunch of fractions, but it doesn't add up to a fraction. It adds up to something like in fact, this series here, -1 to the n over n equals, I think it's minus ln2 or something like that. It's like this crazy thing where you're adding up a bunch of fractions, but you don't get a fraction as the answer, right? And notice that if you were to put absolute values around each term, so I go back to that series, -1 to the n over n, and I put absolute values around it, then that would just means I now have a bunch of pluses everywhere. That is actually the same as the alternating series test. That is the same as the harmonic series. And this diverges. And you can tell that this diverges because it's harmonic. You can also say it diverges because of the p-series test. But either way, this tells you can conclude that this guy, minus 1 to the n over n, converges conditionally, with emphasis on conditionally. Right, so we saw last time I gave you a definition about the different kinds of convergence. Was that last time? I knew it's here somewhere. Right. So I mentioned if you have a series and you put absolute values around it and it still converges, you can say the thing converges absolutely. If the original series converges, but the absolute value series doesn't, then you say it converges conditionally. That's the situation we are in here. So the original series, which is this guy, converges. We can prove that it converges by the alternating series test. However, if I put absolute values around it, I get something that diverges. So here you would be able to, you would say this guy converges, but it converges conditionally. It does not converge absolutely. So this is an example of such a thing. Okay. So that leads us here. We have, yeah, the ratio and root test will probably need some more time for those. I'm also going to talk more about absolute convergence versus divergence. But at this point, as promised, we're entering the last hour of class. So I guess I kind of want to open it up for questions. If you guys don't have questions, that's also fine. I'll just continue because as you can see, I already have a plan for where we're going. But yeah. So I guess we will do that. So are there any questions that you guys want to ask me, or should I just continue? Like from the practice exam, anything you were practicing, and you want to ask me about? And I'd probably prioritize like the practice exam. So, I mean, if you have questions on homework, I would consider that less priority. You could email me about that one, but unless it's sometimes an over integration when the integral upper bound is e and the lower bound is 1. What do you mean? You just apply the fundamental theorem of calculus. Like, what is the question exactly? Oh, you have to tell, like I gave like 5 exams with a bunch of problems. Like I don't know all of them by heart. You kind of have to tell me what the problem is. Like I don't have like all, I don't have all the exams like memorized. Oh yeah, this is problem 5 from practice test 3. Like I'm not gonna know. So you have to be a little bit specific. So I guess what I can do here is I can put some space. So let's do Q&A. X squared minus 1 over x. Oh, let me see here. So writing in the chat. X squared minus 1 over x between 1 and e. Is that the question? Oh, well, I mean, this is just one where you would remember it's an integral. So we have a strategy for it. So the first thing you look, is it a basic rule? No. So the next thing you're going to think about, well, can I simplify it to look like a basic rule? There's only a single thing in the denominator. So my immediate thing that I would probably try was just divide that into each term. So this is just the integral of 1 over e. That would just be x minus 1 over x, which of course, you can think of this as two separate integrals. Each of these are a basic rule now. They're all just power rule. So I add 1 to the power, divide by the new power. And then the 1 over x, I know that that is just ln, the absolute value of x, going between 1 and e. And so I can plug in e for x minus plug in 1 for x. Now, log of 1 is 0, ln of e is 1. And so we'd have e squared over 2 minus 1 minus a half. So that would be the answer there. Yeah, no, U sub would be the third thing you think about, but the second thing we think about worked, so we don't go there. Any other questions? No? So you're all gonna get 100 on the test, huh? Nothing challenged you, nothing stumped you, aside from this integral. Okay. I don't remember which practice exam this is for, so I can't really give you a reference, but maybe I'll look at it later and see where that came from. But I guess we'll just continue. Okay, so test 8. Okay, so there's a test called the ratio test. And the test is so called because you actually create a ratio and based on that ratio is what you're going to make some determination on. So this, by the way, it works for any series. The only requirement is that none of the terms are 0. Right, so that's the only requirement. It doesn't, you don't really care about it's decreasing and you don't have to check anything else. Just make sure that this thing is never going to be 0. That's all you need to worry about. Okay, but generally otherwise this works across the board, right? So it doesn't have to have a very specific form. There are tests where you have to have a very specific form, like a geometric series test requires a very specific form to apply to. To some extent, the alternating series test has a specific form. That form is an alternating sign. Most of the time, this is going to be done with like a -1 to the n or a -1 to the n plus 1 or something like that. And you can alternate the sign. But yeah, the ratio test applies to anything. Okay. Another thing that's really nice about the ratio test is when it gives you convergence, it gives you absolute convergence. So that's very nice. So if you want to talk about absolute convergence versus conditional convergence, once you do a ratio test, you know you get absolute convergence. So you don't have to worry about, oh, is it conditionally convergent or can I rearrange the terms or whatever? No, if you use this test on someone and tells you they converge absolutely. So that's very nice. Okay. And the test is the following. You will set up this limit, right? So you're going to go to the expression for the sequence that you're summing. You're going to replace all n's with n plus 1. So you're going to get an expression. Then you're going to divide that by the original expression. Then you're going to put absolute values around this and take a limit. And because you're putting absolute values around it, it means that you're only looking at magnitudes. You don't have to worry about anything like that. So essentially, now you take the limit of this as n goes to infinity, and that quantity you call L. Now, based on what L does, you can actually make a conclusion, and it's all around 1. So if the limit that you found is less than 1, and obviously it's going to be greater than or equal to 0 because we're taking absolute values, but if the limit is less than 1, then this series converges, and it actually converges absolutely. If that limit is greater than 1, then the series diverges. If the limit is equal to 1, then no conclusion can be made. And there's a very important example or a class of functions. I don't remember if I put that in the notes. Yeah, so this is a very important test in general. I will make an extra remark here because it doesn't work on a general, it doesn't need a general special form to actually work, but there's actually a form where we know it won't work, so don't even think about trying it. And it's a very common kind of function. I do want you to note this test would not work if an is a rational function. And remember what rational function means, the ratio of polynomials. And why? You would always get 1. Right? Remember, when we're taking ratio of polynomials, take the limit as you're going off to infinity, what do you look at? Only thing matters is the degree of the numerator and the degree of the denominator. If you replace the variable with the variable plus 1, you don't change the degree. The degree of the polynomial is going to be the same. Like if I have x squared versus x plus 1 all squared, they're both second degree polynomials. So the degree is not going to change the limit of the function in this scenario. So if you see one of these expressions, like for example, we had one earlier. Where is it? Like this guy. Like if you see this guy and ask you, does this converge or diverge? You would not try the ratio test, right? Like it's going to be pointless. It's going to be a waste of time. Because if I replace all n's with n plus 1s here, I don't change, the numerator becomes n plus 11. It's still a first degree polynomial. The denominator is going to become n plus 1 squared plus 2 times n plus 1 plus 3. It's still a second degree polynomial. And when you're going off to infinity, with a ratio of polynomials, we know the only thing that matters is the highest degree of the degrees of the numerator versus the denominator. If the degree of the denominator is bigger, it goes to 0. If the degree of the numerator is bigger, it goes to plus or minus infinity. If the degrees are the same, it'll go to the ratio of leading coefficients, right? So when you do this and you divide by that, the degrees are going to be the same because replacing n with n plus 1 is not going to change degrees. So when you take the limit, you're always going to get 1 as the answer. And for the ratio test, 1 is inconclusive, right? So while there's no, theoretically speaking, there's no restriction on what you can use this test on other than just making sure none of the terms hit 0. But an artificial restriction is don't use it on a series that's a rational expression because you're not going to get anywhere. You're just going to waste your time getting to a point where you're like, well, no conclusion, guess I should try something else, when you should have known that from the beginning. So that's something I just want to mention. So you'd always get L equals 1 in a rational. So if you throw in the harmonic series into this, right, the limit would be, so if you have, maybe I'll do an example. So if my series is 1 over n, right, where my an is 1 over n, right, n goes from 1 to infinity. Then if I get an plus 1 divided by an, that's good. It's going to be 1 over n plus 1 divided by 1 over n. That's going to be n over n plus 1. And so that would approach 1, right? Because the highest degree in the numerator and denominator is 1. So it goes to the ratio of leading coefficients. And so in this case, you get your L equals 1. All right, we know this diverges, right? We know this diverges. Now, what would happen if I use this on 1 over n squared? So here, if my an is 1 over n squared, then my an plus 1 over an, and yes, technically I'm taking absolute values around this, but it doesn't really matter. If I take that, that is going to be equal to 1 over n plus 1 all squared divided by 1 over n squared. Well, that's just going to be n squared divided by n plus 1 squared, which is a second degree polynomial divided by a second degree polynomial. As we're going off, as n is going to infinity, this goes to the ratio of leading coefficients. The leading coefficient in the top is 1, the leading coefficient in the bottom is 1. So this goes to 1. So this means your L is 1, but we know this converges. So when your L is 1, it can go either way. You won't know. And it turns out when you have a rational expression, your L will always be 1 because plugging in n plus 1 will not change the degree. So that's one thing I would mention extra about this guy. Don't waste your time using it on guys like that. And in fact, I will tell you when you want to use certain tests, we're actually going to talk about that. But it's also actually in the table. So in that table I gave you guys in the notes here, it does give you some ideas. So like the ratio test, you'll see here that technically speaking, it can work on any series. You just need to, it should say any series where an not equal to 0 or something like that. Technically it can work with any series as long as you're not dividing by 0. The only thing is, it's especially useful when you see exponentials or factorials. That's when it really shines, right? That's when you can kind of hint. So you're looking at something, okay, it's not a P series. I don't know what to compare it to. It's not geometric. My integral test isn't going to work. I don't know how to use the comparison theorems because I don't know what to compare it to. And, you know, it's not alternating. I don't know what's going on. But you notice, oh, there's an exponential function here, or there's a factorial. The ratio test might be something that could work. And so that is something that we'll go over again, but I just want you to be aware that it's particularly useful when you see exponentials and factorials. So when you see like here, This guy is n over 2 to the n. And it's alternating. Now, the problem asks us to determine whether the series converges absolutely. Okay. Which means I would not use the alternating series test here because it doesn't tell me about absolute convergence. So while this is alternating, would not use alternating series test. Because we want to check absolute convergence. So that's the first thing. Okay. So now we know that we want to use the ratio test. We're in the ratio test section. So I'm just going to show you how this would work. You want to actually construct this L. So here, your AN is -1 to the n over 2 to the n, and your AN plus 1 is obviously going to be -1 to the n plus 1, n plus 1 over 2 to the n plus 1, right? And we want L equals, the limit of AN plus 1 over AN, which from now on, I'm just going to kind of skip a step because technically it's going to be keep, change, flip. So we kind of already know that. So I'm just going to always think of this as AN plus 1 times 1 over AN. Right? Because algebraically, it'll be a lot nicer. So you just know you're going to take the AN plus 1 guy and then multiply it by the reciprocal of the AN guy, right? And that's a step you'd have to do anyway. So I think it's just nice to just do it all in one shot. So yeah, so that brings us to L equals the limit of AN plus 1 over AN, which I'm going to write as AN plus 1 over 2 to the n plus 1 multiplied by the reciprocal. So this is like -1. It's like 2 to the n over -1 to the n times n. Okay. Now, I'm going to make some comments here. Here, it's probably, you can probably see it, but generally speaking, I would say to make sure that you're not making any algebraic mistakes or any silly mistakes, it's generally nice to kind of put the same types of functions together. So you want to group the exponentials, group the polynomials, group all the different kinds of functions and kind of put them together. So this is technically optional, but recommended. To write this as, okay, I'm going to take the alternating parts and put them right underneath. Then I'm going to take the polynomials, put those together. Then I'm going to take the exponentials, put those together, right? So product of fractions, as long as the denominator stay in the denominator and the numerator stay in the numerator, I can move the factors around. So I can swap the positions and I can separate them into fractions. And that's going to be nice because now one thing you can see is that things will actually cancel pretty nicely. So this will cancel into that. This will cancel into that. And so you really end up with, sure, it's an absolute value. So this would be, the -1 is going to disappear. We're just going to have n plus 1 divided by 2n, right? And now you can realize here, like the -1 will will disappear. I don't know if you, how you want to put it. Disappear because of the absolute values. So I would go further to say, because of this, you can even ignore this part. So what if you know you're going to use the ratio test, you can actually ignore anything like that. Anything that alternates a sign, you can ignore it, because what you'll realize is that it's going to cancel out in the alternating in the ratio test in such a way that you only get a -1 factor left over, right? So the alternating factor could be left out in the beginning. Right, so that's just a pro tip. So you could have even gone through this and just ignored that part. It wouldn't have made a difference. And I find, generally speaking, sometimes things will look more complicated than this, and students will make mistakes with the algebra. You tend to make less mistakes with the algebra if you just separate things in your head. Okay, put all the exponentials over here, put all the polynomials over here, put all the guys over here, and you kind of separate them. Anyway, we know that how polynomials would behave, right? Because the degree of the numerator here is the same as the degree of the denominator. It goes to the ratio of coefficients. So that this limit is actually 1/2. And by the way, 1/2 is less than 1. So you end up in a situation where L is less than 1. And so according to this, our series will converge absolutely. Absolutely converges. Okay, so that is an example of the ratio test. Right, so generally it works on anything as long as the thing that you're looking at will never be 0. And here you'll notice that it starts from n goes from 1 to infinity. So the n is going to be 1, 2, 3, 4, blah, blah, blah. This will just be your numerator, right? The numerator never hits 0. So this fraction will never hit 0. So we know we can use the ratio test. And things group in a very nice way. Ratio test is going to be something that a couple of reasons you would use it. One, if none of the other tests works, none of the easier tests work, and you want absolute convergence. So these are the two main reasons. It has exponentials or factorials in it, because factorials also behave very nicely under this test, because when you increase a factorial by +1, you can actually cancel out factorials and then you don't have to deal with them. But we'll see some examples of that actually. In fact, I think the next example has a factorial in it. So here's the next example. So I'm just going through because no one wants to talk to me. So, all right. So for whatever reason, I come to the conclusion here that I want to use the ratio test. And so I'm, of course, once I decide that I'm going to use the ratio test, I'm immediately going to look at L. L is going to be this. So that's going to be, I'm going to look at the original. I'm going to ignore the -1 to the n. I just explained that we can ignore that. So I'm just going to jump in and replace n with n+1 everywhere. And then I multiply by the reciprocal of the original. So that's just e to the n over n factorial. Now I'm going to take my optional step. I'm not going to try to be a hero or anything. I'm just gonna, take my time. Separate the exponentials from the factorials. Now, let's actually talk about this. So the exponential parts you should be able to deal with relatively easy. So we know that's going to be, this is going to end up being a 1 over e over here. Now, for the factorials, here's the reason why factorials work out nicely. So if I look at this part here, n plus 1 factorial divided by n factorial. Okay. Now remember what factorials are. This is just the product of all things from that going all the way down to 1. N factorial is the product of n. All integers, all positive integers going down to 1. You will notice that one factorial is included in another one. All bigger factorials include smaller factorials. So when you increase the factorial by putting a +1 on one of the parts, you've actually ended up in a situation where the smaller factorial is going to be included in one of the bigger factorials. And so that's actually going to put us in a situation where a lot of things will cancel out. In fact, n plus 1 factorial, you can think of this as n plus 1 times n factorial. And then the n factorials will cancel out. So this whole thing goes to n plus 1. So here's another example. Let's say I had an expression with, my an looks like, let's say 2n plus 1 factorial. So then if I look at an plus 1 divided by an, what would happen? This would be 2 times n plus 1 factorial divided by 2n plus 1 factorial. So this is actually 2n plus 3 factorial divided by 2n plus 1 factorial. Now with factorials, what you can always do is you can start at the bigger one and start counting the factors down until you get the smaller one. So 2n plus 3 factorial I know is 2n plus 3 times 2n plus 2 times 2n plus 1. I reached the smaller one. Stop it right there and put the factorial on it. And so that will always cancel out. So sometimes you might have to go several steps, but eventually this thing is going to terminate. The bigger factorial is going to include the smaller factorial, and you can just count down until you hit the smaller one, and then you'll be left over with something nice. So you go from having to worry about a factorial function, which is for a calculus class, it's a very complicated function really, to a quadratic, right? So that's why the ratio test is so nice with factorials. It can actually reduce them to polynomials essentially, right? So this n plus 1 times n factorial, this will actually simplify to n plus 1 because by this calculation here. And so now I'm taking the limit as n goes to infinity of n plus 1 over e. And obviously that goes to infinity because my n is in the numerator. It's going to infinity. E is just a number, it's a constant. And oh, by the way, infinity is greater than 1. It's a lot greater than 1. So this tells you that the series diverges. And you can say by the ratio test. Because we are in a situation where our L is greater than 1. So our series is going to diverge. By the ratio test. super excited about that. So now, I will mention here, ratio test was overkill. Because if you actually looked at the limit as n approaches infinity of this guy, n factorial over e to the n, that goes off to infinity, which is not equal to 0, which means that the series would diverge anyway. Right. The top is a factorial, the denominator is an exponential. Factorials beat exponentials. We looked at that. I want to say we did that yesterday. Yeah, right. Factorial compared to an exponential. I'm comparing e to the n to n factorial. The n factorial is much bigger. So if the n factorial is in the numerator and e to the n is in the denominator, that goes off to infinity. So if I just gave you this series on a test, for example, you saw this series come up, like I would not do the ratio test because you'd have to go through all of this. It's actually pretty easy to see that the limit doesn't go to 0. And so you can actually know divergence from early on. Right, I'm just going through this as an example of the ratio test because I wanted to show off this whole factorial trick. But technically speaking, this is better. So this would be better to do than this would be better to do than the ratio test in an exam. Right, so I just want to mention that, like, this is just for illustration purposes. Right. If this guy randomly showed up in front of you, like you wouldn't go ratio test. It's overkill. You're working too hard.
Sorry, I had a question.
Yes.
Could you go over again how you did the breaking up of it, like the n+1 factorial over e to the n+1? Like how do you break that up?
You're talking about this line? Like how did I get that from the previous line?
No, the one above it. The line above it, yeah.
Oh, how did I go get this line? So here your an is just the original guy, right? So this is just your -1 to the n over, well, I'll look at the an as the part without the -1. So this is just n factorial over e to the n, right? And so an+1 just means I go to that formula and I replace all n's with n+1s. So everywhere I see n, I put a parentheses and put n+1 inside. Right,
Oh, okay,
and then
thank you.
and so then when I take an+1 divided by an, it's the same thing as taking an+1 and then multiplying by the reciprocal of an. Right, so that would mean I would take the n+1 factorial over e to the n+1 and then multiply by 1 over n factorial over e to the n, but that just keeps change flipped kind of thing. Right, so I just write the original guy upside down. Right, and that's what brought me here.
Okay, thank you.
Yeah. So the an+1 is literally when you go into the formula and you replace the n with n+1. Right. So everywhere I see n, plug in n+1 instead. And it's very important. So I did an example here. It's actually very important that you do this in parentheses because, like, So 2n, for example, becomes 2n plus 2 because you have to replace the n with n plus 1. So you have 2 times that, and it would actually distribute. So I would get 2n plus 3 here, ultimately. So everywhere you see n, you kind of imagine parentheses around it and then plug in n plus 1. And that is your an plus 1. Okay. Okay, so thank you for your question. Any other questions? This brings us to the 9th test, the root test. And there's another important remark here. The ratio test and the root test, they go, I don't know if I want to mention that. Well, I can actually literally read this to you because I'm doing this thing. So there's another test called the root test, where you're taking the nth root of something, right? Which is, it kind of tells you when this would be useful, right? If you have something like to an nth power, right? You would want to like get rid of the nth power and get something nicer that you can deal with. So there's something called a root test where you can actually judge by looking at how the nth root of the absolute values. So you want to put the thing in absolute values because you don't want to get like complex numbers. If this guy might hit negative numbers and your n happens to be stuck on an even thing, then all sorts of things could happen. So you put things around absolute values and you take the nth root. And again, this can work with any series, technically. There's no real restriction on the series because you can just take the absolute value of something and take the nth root of it. No one's going to bat an eye, like, okay, that's fine. Like, and nothing can stop you from doing that. However, the conclusion is very similar. If you look at that limit and your L is less than 1 after taking that limit, then you get absolute convergence. If your L is greater than 1, then the series will diverge. If your L equals 1, then no conclusion can be made. And the thing is, we actually know that the ratio test and the root test, you know, they're best pals. You know, they're two peas in a pod, and they actually behave similarly in the sense that when one is inconclusive, the other one will also be inconclusive. So if something can't work with like if something won't work with the ratio test, then it's not going to work with the root test. And if something doesn't work with the root test, it's not going to work with the ratio test. So you might be in a situation where you try the ratio test or you try the root test and you realize, oh, I can't really make a conclusion. So if you try the ratio test and you can't make a conclusion and you want to pick some other test to try, don't pick the root test. Like the root test and the ratio test will always give you the same conclusion, actually. Like the root test will always give you a less than 1 when the ratio test does. It'll always give you a greater than 1 when the ratio test does. It'll always give you equal to 1 when the ratio test does, and vice versa. So they actually go hand in hand, right? So I did make a comment here, right? So if one is inconclusive, the other one is going to be inconclusive. So if you try one and it doesn't work, you don't want to try the other one. It's actually going to be a waste of time. You're going to try one of the other 8 tests that I told you about. And remember that the ratio test, as I mentioned above, it's not useful when you're using it on rational functions. The same thing is is true here. So I underlined it in red. The ratio and root test, they're useless when it comes to rational functions. So if you have a rational function, do something else. Okay. And I pretty much explained in words here what I explained verbally, so I'm not really going to read over here. I said everything I said here verbally. I just wanted to make a note of it somewhere. So here is an example. So we have this thing And we have like this nice little thing raised to the nth power right here, right? So that kind of hints to me that, oh, the ratio test might be something that's nice to use because I can get rid of that nth power. And so I can apply that. So if I set my an equals 2n plus 1 over 7n minus 3 to the n, I can apply the ratio test, the root test. Take the nth root of an in absolute values. Because I don't really want to worry about, oh, this might be negative somewhere. So for example, if this series starts at 1 to infinity, if I plug in n equals 1, notice that this is negative, although the first root wouldn't really deal with that anyway, but just as a precaution, you always put absolute values around it, and that's what gives you the absolute convergence in the end of the day. So this would just become the limit of the nth root of the absolute value of this thing to the n. That's 2n plus 1 over 7n minus 3. So of course, the n cancel this, and you're just end up with the limit of 2n plus 1 over 7n minus 3. You now have a rational expression. You're taking the limit as you're going off to infinity. So we know that only the degrees of the numerator and denominator matter. They're both first degree. So when the degree of the numerator and denominator are the same, it goes to the ratio of the coefficients. So this goes 2 over 7. And you might notice 2 over 7 is less than 1. So we can say, the series converges absolutely by the root test. And it's just called the root test because you take the nth root. So the root test is particularly convenient if you have something raised to the nth power. And then you can do the root test. All right. So there's one other concept I want to talk about. So technically in that table that I gave you guys yesterday, they're like 10 tests, 10 rows. But it talks about, one is actually just mentioning what absolute convergence is, right? Which I can just give you in a definition. But an important problem type that I'm going to ask, did I put this as a bonus problem? I think maybe I did. An important question that I could ask is ask you to talk about series converging and particularly what kind of convergence. So there's a problem type where the question is, determine whether the series converges absolutely, converges conditionally, or diverges. So you have to answer it in a very specific detail. If it converges, you have to say what kind of convergence and so on and so forth. So the absolute convergence isn't really a test per se. It's more just like a check that you want to do. But other than that, we covered all the tests. Right? And this is just something that I want to explain as like a concept, which is what these words are about. Right? So we know absolute convergence just means that if I throw absolute values around everything, it still converges. And this is like a gold standard of convergence. This means that the thing converges so strongly that even if we rearrange terms, it's not going to matter. It's going to add up to the same thing. So that's absolute convergence. So there are going to be times where I'm going to want to ask you to talk about when something converges absolutely versus conditionally, because in the calculus context, it's actually very important. So it turns out just by looking at the concepts of what absolute convergence means, there is a process that actually makes sense when you are asked that specific kind of question, right? If I'm asked you, oh, determine whether this series converges absolutely, converges conditionally, or diverges. That's the problem type. There is a way you want to approach this. So step 0, which is true for every series, always try to apply the test for divergence first, right? So if the test for divergence tells you it diverges, you stop, it's over. You don't need to check any convergence. If the test for divergence fails, there is nothing else to talk about. So you always do that as step 0. So you try the test for divergence. So that's always step 0, right? If it's found to diverge, you stop, you say the series is divergent by the divergence test, and then that's it. If the divergence test is inconclusive, that's when you move on to step 1. Now, step 1 says you should check absolute convergence first. Because if it converges absolutely, it automatically converges conditionally. You would not have to check conditionally in addition to checking absolute. Once you have absolute, you have everything. It's the gold standard. However, if you check conditional first, then checking absolute is an extra check. So you can kind of turn your work into double what you have to do. So if you do a test that tells you conditional convergence, then you'd also have to do another test that tells you absolute convergence. It's better to just start with the absolute convergence first, because then if that works out, you won't have to go to the second one. So the next thing is to check absolute convergence. And this is actually not bad. All you do is put absolute values around everything. So if something is alternating, just ignore the -1 to the end part. Just ignore the alternating, and then check if that series converges through one of the tests. And then that would give you absolute convergence. So you just go through and you put absolute values on everything and see if the thing converges. If it does not, if this series diverges, which just means the absolute values around it causes it to diverge, it might not diverge in general. At this point is when you'd move to the next step and check conditional convergence. So conditional convergence means you take the absolute values back, right? Put back the series as it was originally and try to do a test on that series. So if it was alternating and you ignored the -1 to the end and it didn't work out for you, now put the -1 to the end back and run another test on it. Usually it's going to be like the alternating series test. And if that converges, you can make a conclusion. So the idea is you'll apply the test for divergence first. If this equals to 0, you have to move on to the next step. If this not equals 0, you're done. You say, okay, it diverges by test for divergence, the problem ends. If it's not 0, you have to move on. Here, now you throw absolute values around everything and do a test for convergence. If it converges in this case, you say the series converges absolutely by whatever test you used, right? If it doesn't converge in this case, then you would say nothing, you move on to the next step. Then you take away all the absolute values, you look at the original series and you check if that converges with another test. If it does converge in this case, then you say, oh, the series converges conditionally by whatever test you used. If it doesn't converge in this case, then there's no chance for it to converge ever. And you can actually stop the process now and just say the series diverges. So there's like a 3-step process where the first step is step 0 because it's the trivial step. And you might not have to do all 3 steps, but you kind of want to go in this order, because if the first one works out or the second one works out, you won't have to do the third. So if you do it in this order, it's a good order in which to do it. Statistically speaking, you're going to do less work by doing things in this order. So I'm not going to do any examples, especially since we're way past the test material, but I left some examples here for you to try. And we'll actually pick up with these examples on Monday. But yeah, we kind of finished talking about series tests. Yeah, that's it. So any questions before we go? Does anyone need to ask me questions in like a short office hour or something like that, or are we cool? So remember the test is actually posted. It's been posted for a few hours now, about 6 hours now. And it's going to be up for another 24 hours from now, which means you want to start it in like 22 and a half hours from now, the latest. The test is going to be due tomorrow at 9 p.m. So make sure you do it before that. Going through the practice tests will prepare you if that all goes well. And that's that. I guess if you have any questions for me before you take the test, that's fine. You can email me, and hopefully I'll try to pay attention to my email. So I probably won't be answering emails for much longer tonight, but tomorrow I'll keep my eye out on my email. But yeah, that's it for today. There's actually a lot more to do with series, but we're essentially up to section 11.6 now. Like 11.6 really just goes through all of these tests up to 11.6, and then we start doing other things with series. So yeah, I guess that's it. It doesn't seem like anyone has any questions, so I will let you guys go. Have a good night. Good luck on your test. And I will see you guys in the next one. Ciao.